Okay, hello. So today I'll be presenting this paper, PoseFix, Correcting 3D Human Poses with Natural Language, published in ICCB 2023. So at its core, what this paper does is it maps between two different poses using natural language. So let's say we have a pose A, a source pose, and a pose B, a destination pose. This paper maps between these two using this text, which describes the changes needed in pose A to reach to pose B. The contributions of this paper are as follows. They introduce the PoseFix dataset that associates pairs of 3D human poses and human written textual descriptions of the descriptions. And they introduce the task of text-based pose editing that can be tackled with a conditional VAE pipe baseline, and studying the task of correctional text generation with a conditioned autoregressive model. So first, they introduce this PoseFix dataset to tackle the two pose correctional tasks considered in this paper. The new PoseFix dataset is considered. The total size of this dataset is 135,000 triplets. So the triplets are, there is pose A, the source pose, pose B, the destination pose, and the text modifier, which describes how to go from pose A to pose B, the changes needed in pose A to reach pose B. And the 3D human body poses were sampled from AMAS. So AMAS is a collection of data sets where each data set is a sequence, a video sequence of a human doing something. So to make this PoseFix data set, they choose samples from AMAS sequence, sometimes from the same sequence, which they call in sequence, at 0.5 second apart. Sometimes they are sampled from different sequences, which are out of sequence, meaning different videos. So and so this data set has two parts. One from the 135K triplets, 5K comes from human, 5K are from human annotations, and 130K are automatically generated captions. So for the human annotated part, they collected the textual modifiers on Amazon Mechanical Turk from English-speaking annotators with a 95% approval rate, who already completed at least 5,000 tasks. The annotators were given the following instruction. You are a coach or a trainer. Your student is in pose A, but should be in pose B. Please write in the instructions so they can correct the pose on at least 3 aspects. And before we get into the automatic pipeline for PoseFix, it heavily relies on the automatic data pipeline from another paper, PostScript. So I'll briefly talk about PostScript first. In PostScript pipeline, they take as an input 3D human body skeleton, and then they calculate these things called postcodes, which are some elementary measurements taken on the body joints. So there are 5 kinds of postcodes. First we have the angle postcode, which is the angle formed between 2 different bones, and distance postcode, which measures the distance between 2 different joints, and relative position in 3 axes, which measures basically whether the joints along those axes are in front of each other or behind each other, to the right of each other, to the left of each other, above each other or below each other, such kind of relationships. And then there is pitch and roll, which measures the angle formed with respect to the y-axis. And then there's ground contact, which checks whether the part of the joint is touching the ground or not. So these elementary measurements are taken on individual joints, usually, or between 2 joints. But they can be combined into super postcodes. So super postcodes are unlike postcode, which are defined between one or more joints, one or two joints. Super postcode is made up of multiple joints describing a single body part. For example, super postcode could be describing the whole torso or sometimes the whole body instead of just describing two or more joints. So in case of super postcode, for the defined body part, there are some underlying joints in that body part. If they meet certain values, for example, for the body to kneel, to say if the body is kneeling or not, the knee has to be bent. Both the knees have to be bent. Such kind of relationships they check for. So those are super postcodes. And after the super postcodes, there's the postcode selection step where they get rid of basically unnecessary postcodes or trivial postcodes. And then postcode aggregation, I'll talk more about it later, but postcode aggregation, what they do is multiple single line sentences which can be expressed together, maybe joined together or joined together and expressed in a single sentence. And then comes the postcode conversion part where another thing I didn't mention is these elementary measurements are, depending on which threshold the elementary measurements are falling into, they are assigned some category labels. For example, in this case, the angle is assigned the label bent at right angle, and the distance is labeled Y. If the distance was higher, maybe it would be shoulder width part. If the distance was lower, it would be maybe close. So these category labels are then in postcode conversion step. We have predefined template sentences with blanks. So these blanks are replaced by these category labels to form complete sentences. And then the complete sentences are concatenated together to form the complete caption. Now for the automatic data pipeline in PoseFix. So in PoseFix, instead of postcodes, they have pair codes. So, and instead of one human body joint as an input, one human body skeleton as an input, we have two human body skeletons, the source pose and the destination pose. So for angle, pair code, they measure the difference in the angle between two bones, between the source pose code and the destination pose code. They do the similar thing in distance, the difference in the distance between two joints in source pose code, in the source skeleton and the destination skeleton. And relative position is also just the differences between the two skeletons. And similarly, they are also assigned some category labels. And then instead of super postcode, they have super pair code. And in super pair code, besides the elementary pair codes, they also take in PostScript postcodes when assigning labels to the super pair codes. And similarly, we have the code selection step, where randomly unwanted pair codes are dropped. And then comes the aggregation part. So first we have the entity-based aggregation, where this, for example, for an organ that is made up of two or more joints, if all the joints in that organ or part of the body is doing the same thing, they are expressed in the same sentence. So instead of saying move left hand to the left, move left elbow to the left, they just say move the arm to the left, since hand and elbow fall within the arm. And then symmetry-based aggregation, where the part of the body that is in opposite sides, if they're doing the same thing, they're expressed together in the same sentence. So move left arm, move right arm becomes move both arm. And key point-based aggregation, what happens is for a particular joint that is involved in two different actions, that instead of having two separate sentences saying this arm is doing this and this arm is doing that, they have a single sentences just concatenated using the and word.
So
And
is this which part is actually the most distinct part compared to the PoseFix?
Instead of most distinct part would be this part. You mean in compared to PostScript? It would be this part. In PostScript, we have just a single person, and we take measurements, and we measure angle distances between joints for the same single person, and we record those. But in here, we measure between two person. So we measure the angle of this person first between the same joints, and the destination skeleton second between the same joints. And instead of reporting the angle values we measured the difference in angle between the two. So the difference between two skeleton would be what sets it apart from PostScript. And yeah, that's the main difference. And then comes we have the interpretation-based aggregation, where same action being performed by two different joints are expressed in the same sentence. And then comes the code ordering step, which is also not in PostScript. They introduced it here. So here what they do is, this is just so that when describing the, in the caption that is formed, when describing multiple joints, the joints that are near to each other are described one after the another instead of being scattered throughout the caption. So the way they achieve this is, first they define the body in a graph structure, the joints which in reality are adjacent to each other are connected to each other in the graph structure. So they start off at some joint, and they, from the other nodes that are connected to that joint, they pick one joint randomly, and then whichever node is connected to that joint, they pick one of those randomly until they reach a maybe leaf node where it's not connected to anything. And then once the leaf node is described, they go back to the previous node and repeats the same process basically in a depth first manner. So this is just to give the descriptions in an organized manner, that's all. And then we have the code conversion, which is the same step. We have some predefined sentences, templates with blanks, and those blanks are filled after selecting the subject and adding the conjugate verbs. And finally, we have these sentences are joined together to form the complete caption. Now comes the part for application to text-based pose editing. Here they introduce a VAE baseline to perform text-based 3D human pose editing. So the aim is to generate new poses based on two input elements: the initial source pose A that provides some context, and the textual modifier which specifies the changes to be made. So the goal here is to take one pose and some change in the text as input and output the resulting or the destination pose. And here's the architecture. So first, the source pose and the destination pose are passed through the pose encoder, a shared pose encoder. So for pose A, we get this vector A, feature vector A, and for pose B, we get the feature vector B, and the text caption is passed through frozen distilled bird, which is then passed through transformer blocks followed by average pooling to get the M feature vector, and then the A feature vector for the source pose and the M feature vector describing the changes needed are sent through the fusion module, and which results in this P vector. This P vector is then fed through two fully connected layers to get the mean and variance for the prior distribution. And for the above, we have the P vector from the destination pose, and they are passed through, similarly, they're passed through the two FC layers, which give the mean and variance for the posterior distribution. And then during training, KL loss is applied between this posterior and the prior distributions. And during training time, they sample from the posterior, and they pass through pose decoder to get the generated pose B hat. And then reconstruction loss is taken between the ground truth destination pose and the generated pose B hat. But during inference time, the sampling is done on the prior distribution. For the pose encoder, they use the V-poser architecture. And for the text encoder, a transformer followed by average pooling, processing frozen distilled word embeddings is used. They also use another setup, which I'll describe later. And for the fusion module, they use an architecture called TIRG, T-I-R-G, which is well-spread module for compositional learning. It consists in a gating mechanism composed of two multi-layer perceptrons, F and G, balanced by learning scalars WF and WG, such that this P vector comes by passing the A and M through the F multi-layer perceptron, multiplied by WF, multiplied by A, plus AM being passed through the G multi-layer perceptron, multiplied by WG.
But what is the purpose of this method? So where the pose A and B come from?
Pose A and B come from?
Yeah.
Pose A and B are, so the data set that we created, PoseFix. So what PoseFix did was they took two different poses, pose A and B, which are already existing.
But I mean, the aim of this pipeline is to generate pose B.
Yes.
From pose A.
Yeah, pose A and the text.
But pose B,
yes,
is also used as the input to this system.
During training time, yes.
During training, but during testing, we use only the below.
Yes, the below part. Pose A and the text.
The text description that is describing something about pose B.
Yeah, how to change pose A so that it may matches pose B.
Okay, but I mean, can it be achieved even for the case where pose A and B, so in this case, pose A and pose B are similar somehow?
Maybe in their diagram, it's somewhat similar.
Yeah, but is it applicable when those two poses are different?
They show some examples in the qualitative result where they're different, but if it's too different, they struggle.
But why it has to be similar? Why such condition is used here? What would be the application of this paper?
When choosing the samples, they say we choose for in context sampling, they choose samples that are 0.5 second apart. And the reasoning they give is that if the distance is higher, there could be infinite many positions might have happened between part A and part B.
So what's the application?
Yeah, the application is makes slight adjustment to poses.
Slight adjustment, but during pose estimation or in what situation? Because there are not much situation where such detailed description is available.
So I'm sorry.
So I mean, in for example, if we want to improve the pose estimation pipeline, that estimate images to 3D mesh. Their initial mesh might be not very accurate. Maybe not very accurate, and maybe using this pipeline we can improve them.
Yeah.
Maybe. But we don't have such detailed text description in that case. So, but in which application, in which case that detailed text appropriate is available, and
In which
I mean
case,
that would be some application of this pipeline.
they call this pose editing baseline, so they assume that we know what to do to pose A already.
But I mean, if we want to edit the pose, then why it should be start from similar pose? I mean, it should start from some canonical pose, and given some text description, we have to the pipeline have to manipulate the initial pose.
Well, the use case examples they give is maybe someone teaching yoga, for example, a teacher teaching its students.
So their pose are slightly, I mean,
Different from the
different
teacher's
from
pose.
the teacher's pose. In that case, they want to, I mean, amend those.
Then for training data and augmentation ablations, they take FID and elbow on joints, vertices, and rotations. And they also consider MPGE, MPVE, and geodesic distance. And for these, they sample 30 samples from the prior distribution and take the best of them for consideration here. And so in this one, for this part here, they use in the diagram, they show frozen distilled and transformer, but they also tested with glove instead of distilled and by GRU instead of transformer on the later part. And with or without implies whether it is with or without pre-training. So pre-training, what they do is they have 130,000 automatically generated captions. Those automatically generated captions are used for pre-training, and they use the human annotated ones for fine-tuning. And when it's without pre-training, they only use the human annotated ones to train the network, and they don't use the automated ones for training. So yeah, that's with and without. And when it's without pre-training, distilled plus transformer usually performs better. But when it's with pre-training, glove plus by GRU performs better. And for data augmentation, even with data augmentation, when it's with pre-training, the results are massively better compared to when it's without pre-training. And when they apply left-right flip, which is they change in the skeleton, they change the left side or the left side definitions to right side definitions, and they also change the text accordingly. This also helps in some cases. And in paraphrase, they use instruct GPT to get two paraphrases for the existing caption. And then comes the PoseMix and PoseCopy. I'm not really sure why they configured the PoseMix in this way, but what they do in PoseMix is they also, besides the PoseFix dataset, they also include the PostScript dataset in training. In PostScript dataset, so they take the PostScript descriptions of both Pose A and Pose B. And for Pose A, they make the pose to be 0 and take captions based on 0 pose. But it doesn't help much in PoseMix. So, and what they say is if they do this case, if they train with PoseMix, the model learns to ignore pose A, which is given a pose of 0. To avoid that, they introduce PoseCopy, where the text modifier in PoseCopy, they take pose A and pose B, but the text modifier part is left blank. So the model is forced to pay attention to pose A since they no longer have the text. But I'm not sure why this setup helps or why they applied this setup, but this setup clearly helps as the results show. And for qualitative results, these are qualitative results. To the left, we have the source pose and the text, and then we have the destinations. So the takeaways from this is that some egocentric relations that are simple, for example, raise your right elbow slightly in the first row, are better understood than more complex, particularly contact-based descriptions such as bend your elbow so it's almost touching the side of your knee. And crouching and lying down poses are most challenging, as shown in the last row, right? And the crouch is hardly preserved in the third row. And now for the next task, which is overview of correctional text generation. So the goal in this part is the pose A and pose B is taken as an input, and the goal is to predict the text that maps pose A to pose B. For this, they have an autoregressive transformer based architecture. So what happens here is the transformer's job is to, given the text generated up to time t, its job is to predict the next token t+1. And then after it has predicted t+1, when trying to predict t+2, it takes as an input the text generated up to t+1. So in a similar fashion, the pose A and pose B are sent through shared pose encoder, and the resultant feature vectors go to fusing module and FC layer to form n different tokens. And then they have two options: whether they can use the n as a prompt on top of the text token, or they can use the n tokens from the pose and basically use it in cross attention with the text part in the transformer. And the text, as usual, goes through the embedding layer. Positional encoding is applied to it and goes through transformer blocks to produce vectors of size q. Softmax is applied to get the probability distribution of the tokens, and they choose just greedily based on whichever has the highest probability. They just choose that token. And for loss, they just take cross entropy loss. And this part has already been explained, but in inference time, they just whichever is greedy, they just take the maximum negative log likelihood, whichever has that. They just choose that token, and they append that token to the input of the next to the input in the next iteration. And they do this, so they in inference time, they start off with the EOS token, and they continuously decode words until the EOS token, the end of sentence sequence token, is decoded. And for quantitative results, they take the NLP matrix and reconstruction matrix. For reconstruction matrix, they feed it through the model they proposed earlier in the previous task. And they also take our top KR precision. This random text implies when the generated text is compared with a random text, caption of a random GT case. This is just for sanity check. And original text implies when it's compared with the ground truth, when the ground truth is compared with the ground truth to see if it's 100 for these metrics. And in case of these two options, they see that cross attention does better in general, both in with or without pre-training case. But for augmentation, the left-right helps, the others don't help as much. So that's it for me. Thank you. Thank you for listening. Oh, and we have qualitative results, which the writers claim are satisfactory. So thank you.
So you can start.